here today we are having Dr. Anshu Tomar with us. He's a researcher and he did his PhD from IIT Roorkee, and he did his work in extensive work for the heritage structures and for FRI building Dehradun. So he did some analysis and published many research papers as well as publications. So here today we are having Anshu Tomar with us, and he will deliver lecture on lesson learned from the past earthquakes and some of the earthquake features and how we can calculate the parameters of earthquake. So he will explain you that also, and he will demonstrate one of the numerical problems. So you are all requested to have your scientific calculators with you, and some papers also, so that you can also do the calculation at their end, at your end. So thank you so much. Now over to Dr. Anshu Tomar.
So they can clearly hear me. Good morning all. I'm Dr. Anshu Tomar, PhD Earthquake Engineering Department, IIT Roorkee. Presently serving as Associate Professor and Head, Chitkara University, Civil Engineering Department. Good morning to you all once again. So today I will be teaching you that lessons learned from past earthquakes and computer-based design of buildings. It will be overview of conceptual things which we come across during understanding and analyzing and then feeding the same data into the computer simulations. So unless until we don't have the knowledge of basic concepts, we can't move further with our analysis and computer modeling and further the design part. Building in earthquakes, why do building do the things they do? This is basically force is equal to mass into acceleration. So in earthquake, as we all know, there is a deformation of ground, and which is equal to, due to that reason, there is an inertia force which is being developed due to the structure mass, and that is being applied and multiplied with the acceleration of the ground motion, and that brings the force of earthquake force. So this is the same thing, which is force is equal to mass into acceleration, which we have depicted here as the lateral load for the buildings. That is building at rest, that it starts moving, and that we have the an equivalent lateral force is applied to the structure, which is also known as an inertial force created by building's tendency to remain at rest when it is at rest, and it is starts moving and leaves its original position although the ground beneath is moving. So actually the building is at rest and then ground start moving, and due to that reason then there we have the movement of building also due to the inertia force of the building mass. Period and frequency. So this is very important, that period and frequency of a building. Frequency, that whatever the complete number of cycles are there of vibration per second, that in one cycle at how much time it has been completed by the building, that is that's going to give you the frequency of the building, and the time period which it takes for the building to complete one cycle, and that between two sinusoidal waves, that once a cycle is being completed by the building, that gives us the sinusoidal wave. So as we do in computer modeling of structures, this is the basic thing which we do. If we are not having computer modeling, we can do manually the things, that is analysis part. How do we idealize or simulate a complete building, a multi-story building, into a simple structure? We take the column and the stiffnesses, whatever is coming in between at the slab level. At the slab level, we do the lump mass thing, that whatever at the slab level we are having half story above and half story below is taken as the total mass M, and whatever stiffness we are having in between the floors, that we take as stiffness K. So this gives us the simple model which we can use for our calculation. And in this case, we can simply, if we are having this type of idealized stiffness based and mass based model, we can simply calculate time period using t is equal to 2 pi under root m upon k, where we have the mass also, which is in the form of lump mass, and k also. So now natural period of buildings. So as you know that we have just discussed the frequency and time period. Depending upon the frequency and the time period of the building, every building in its own free vibration response, because when we calculate the fundamental natural time period, we don't take force into account. In that case, depending upon the height, the natural period comes out to be depending upon the story height, or how many stories the structure is. 2-story, 5-story, 10-story. These all the things, whatever is being depicted in this table, are being calculated empirically using the formulas, and it is giving the typical natural period of that particular building, depending upon how many floors of they are. And depending upon that time period, the frequency is being calculated. T is equal to 1 upon F. So this we can use that just using the general idea that how many story building could have what natural time period and what frequency it is going to finally give us. And we can have just a general idea, initial view of the things. As I've shown in the you can see that it is a slower shaking. The arrow shows as the number is increasing because the time period is increasing. Okay. Now again, resonance, that depends upon time period and frequency. Depending upon the natural time period of the building, we have certain time period and frequency. And you also know that earthquake motion is due to the acceleration of the ground shaking. So whatever that acceleration is to having some time period and frequency. Ground is also having some time period and frequency, and our building is also having natural time period and frequency. So they should not match. In case we have out of phase in both the cases, that the ground shaking is at the extreme end and our building is also at the extreme end, that means they both are out of phase at the same time. In that case, there will be a resonance as per our physics law, and that is going to bring maximum damage to the structure because the forces will be very much high due to the resonance part. And the example is being shown using the 1985 September 19 Mexico earthquake, in which the place where the earthquake took place, which is having a natural period of around 2 seconds, majority of buildings that collapsed were around 20 stories tall. That means as we it is not always said that as we presume that wherever the earthquake occurs at the epicenter, there is more damage. It is not like that. It depends upon the frequency. If we are having, because at the place where the earthquake is occurring, their frequency is high, frequency content is high. So in case of short period buildings where frequency is high, in that case the frequency of earthquake both will match and there will be a resonance, and it is going to create more damage to the shorter buildings generally. And as we move out of the epicenter, as we move further away from the epicenter, there is a dissipation of waves, and there is a wavelength increases, and we have the reduced frequency. And suppose we have large multi-story buildings, they are having huge, the frequency is low in that case. So in that case, there will be resonance for the higher buildings, and the more damage will be to the buildings which are higher and which are at a quite low lot of more distance to the center of epicenter. What affects building performance and damage? This is basically the things which we need to keep in mind during the setting the configuration of the building. More things like the shapes. What should be the shapes? What should not be the shapes? If you are following symmetry or you are not following symmetry, your building should be symmetric. At least at both the axes, X and Y. If it is not at least symmetric at one axis, at least it should be symmetric to the other axis. At least it should be there. And if you are not having a building which is exactly symmetric, you can provide the expansion gaps. That is what it is mentioned in this slide, that square or rectangular usually perform better than L, T, U, H plus. That is the reason, that because they are unsymmetric some way or the other. If you compare it with the square or rectangular, although it is not always possible to have a square or rectangular buildings, sometimes we need to have L, T or U or plus type buildings. In that case, you can provide expansion gaps to your buildings. Construction materials: steel, concrete, wood, brick. Concrete is the most widely used construction material in the world. Ductile materials perform better than brittle ones. Ductile materials include steel and aluminum. This you know very well, that ductile materials behave very well because they give, even after earthquake and the performance, if after the initial limit state of the building, they let the building go more displacement as compared to your brittle material, which is going to collapse immediately, and the displacement is reduced. So with ductile material, we can have the collapse limit state. That is, you can have the time to evacuate or something like that, and that come at the design stage. So load resisting system, height of the building, these all are parameters which are going to contribute towards your better configuration and symmetricity of the building. So these are the points which are required to be kept in mind. Load resisting system, that it should be a continuous. It should not be a discontinuous path. Load should follow a particular path, and there should not be any discontinuity with the paths. Height of the building, definitely you are going to keep in mind that what is going to be the natural frequency, time period of the building, and at what place you are locating it. Previous earthquake damage, if there it is in any building, first you are supposed to take care of that at the analysis part also, whatever type of analysis you are carrying out. Then intended function of the building, whether it is hospital, fire station, office building, electricity, telephone. That means depending upon the importance of the building, the category that in which it lies, according to that you are going to plan the location and the forces of that building. Proximity to other buildings, that means the gaps you are supposed to maintain. It should not be too much close. Soil beneath the buildings, that means you are supposed to take care of the geotechnical part of the building. That soil investigation should be there, and it should be proper. Whatever parameters are going to be considered, they should be there. Magnitude and duration, direction and frequency of shaking. Key factors in building performance: good connections. That is for both the cases, but it is more critical in case of masonry, because reinforced cement concrete is in itself is a homogeneous type of material to be used in construction. The basic thing is that we need to transfer the loads from upper level to lower level. Your slab should be able to completely transfer the load to beams. Your beams should be able to transfer the load completely to the columns, and your columns should be able to completely transfer the load to the foundation. Because finally we have to have the soil structure interaction, and through the foundation, that load at that force and that energy of earthquake is going to be dissipated and mitigated to the soil beneath to save our building. Building system and frames. This is basically typical type of RCC frame which we take care of and consider during our any evaluation or initial evaluation of structures that we do in engineering. Frame built of beams and columns, steel, concrete. It could be steel, concrete, wood, masonry, anything, but it is a frame analysis, resisting lateral load by bending of beams and columns. Previous lots of open interiors, provides lots of open interior space, flexible buildings. So it is basic type of configuration which is there in every RCC structure. So as there is, we can see in columns, we are having a little bit of more flexibility because we don't have anything intermediate in between. If you are providing wall, that is brick infills in between, that too, if they are being properly designed and provided, they are going to contribute towards the flexibility of the building. Otherwise, if you are designing an open frame, in that case you have a little bit compared that now the things comes up as we have shown here in this figure, that you have bending profile. So it is also depends upon the fixity which you are considering, whether it is partial fixity you are considering, semi fixity you are considering, or completely free. So depending upon that, you are going to analyze. But here I have shown in this slide that only thing is that this is the basic system we follow in our analysis part, which we use in our day-to-day life. RCC structures and masonry structures. So most of our discussions today will be corresponding to these two types of structures. Steel and other things we are not discussing today. So building systems, brace frame, this is one type of brace frame, that is which we use in, I should say, retrofitting, you can say, or you can also say that it is a system which is being used everywhere nowadays for increasing the lateral load resistance of the building. It is going to, if it is having viscous dampers or fluid viscous dampers in between, and in between these type of cross bracings, in that case, in time of earthquake, the bracing part will be damaged and it will be just working as an electrical fuse, which let itself get damaged and safeguard the building and not let the structural elements of the building be damaged. Although it is in that case, if it is not having fluid viscous dampers and it is homogeneous and it is intact, structurally connected to the structure, in that case it is going to increase the lateral resistance. Building systems, shear walls, that is, shear walls is a system which we use in reinforced cement concrete also, and in masonry systems also. In RCC structures, we provide shear walls completely from bottom of the foundation to the top floor, to the roof. It could also discontinue in between, because as per research, it has been shown sometimes that till 80% of the total height, if you provide shear walls, they are better occupied to have the resistance towards earthquakes. So shear walls in case of RCC are like that, they are reinforced. And in case of masonry, as you know, brick structures are there. Brick and mortar as a unit and constituent are together, forms the walls of houses or buildings. So every wall is a shear wall in that case for the particular type of earthquake direction. So here also it has been shown, you can see that force, the arrow of the force direction, and the movement, the figure shows that it is parallel to that particular wall. So in the particular direction, that shear wall, that wall will be behaving as a shear wall for that particular direction. So every wall which is having earthquake force parallel to it, that wall we will consider as shear wall, and accordingly we will analyze and design that wall, because the wall just perpendicular to that particular shear wall is going to be not participating much for that particular earthquake load which is parallel to that particular shear wall. Because due to that reason, that if whatever I have shown in this figure, the shear cracks which are being shown at the right hand side also in the red color, that cracking around openings, because we are having piers just beside the door and there is a spandrel above. So this type of cracking occurs when our wall behaves as a shear wall. So we need to take care of every wall as a shear wall, so that they should not have cracks, as we have shown here. You can see in the figure that between the windows also there is cross cracking. In this case, whatever pier we are having, it is behaving as a short column, because the stiffness and all those things completely constitute the behavior. Accordingly, the pier is going to behave. So it is going to act as a short column, we say, as we talk in RCC. That wherever we have the shear increases, shear force suddenly increases as the load transfers from top to bottom. It is increasing, and due to the small cross section, it is having cross cracking. Wood frame construction, it is not more important and not more much being used in India right now. It is more used in Japan and other countries where it is famous quite far ancestrally and historically. It is not picking up in India. So most houses and low-rise apartments in California, some strip malls, shear wall type construction, here again the same thing. Whatever material you are going to use, the thing is same. You are supposed to analyze that particular structural element, whether it is of thin RCC wall or it is a wood wall or it is a brick masonry wall. You are going to analyze the forces as a shear wall, and then you are just simply supposed to carry the analysis and design. Lightweight wood is lightweight, that reduces the inertia because force is equal to mass into acceleration. The mass is reduced, so automatically force is going to be reduced. Generally perform well in earthquakes because due to the reduced mass and connection it caters for. Damage often consists of cracked plaster and stucco, which can be repaired in cases of wood. Wood frame damage, we can see here that the type of foundation is being shown and the type of movement is there in the building. You can see on the top right corner, the building is having a movement which is there, and bottom it has been shown the type of foundation. So it shows that it can be repaired to a very large extent. That is why it is beneficial. But in case of masonries, that we can see, because masonry, if you consider it as a non-structural element, it can be done away with. So this is the wood frame damage, cripple wall failure. So type of foundation, we are having same RCC type of foundation, which we can simply anchor to the structure, superstructure foundation, and you can just rectify the alignment which is being changed after the earthquake, and then you can just restore the vertical structural elements which are being connected to the foundation. It is not so, because in case of an RCC and masonry, these things are very difficult to be done with. So although it is difficult in wood structures also, but as compared to RCC and masonry, it is easy. So you can just rectify the things by giving the proper alignment to your structure, keeping the foundation erect, and then you can just, as we do in base isolation, you can just rectify in that case. Soft first story failures. Now we come on to slowly onto the real structural failures of earthquake. What soft first story failures are there? Because most of the time you might have seen that in our multi-story buildings we have parking lots, and in our parking lots what we do, we don't provide the brick infill as a structural element, which can constitute if provided to the stiffness of that particular floor. But we don't provide that brick infill structurally connected to the columns and beams in the ground floor parking slots. Due to that reason, we have immediate story stiffness difference as compared to the stories above. 70%, 80% story difference is there, stiffness difference is there. And as per IS 1893, it is not suggested. If you have a stiffness difference of such a huge amount, that is definitely it is going to be there that your ground story parking lot columns are going to fail. And that will lead to a complete collapse of your building. So it is not suggested, and it is suggested that we should take care of this. As we have shown in this building, that complete collapse is there in the, you can see on the top right corner, a building tilted and fall, even the foundation is not clear. And on the bottom left corner, you can see that it is being damaged. It is the complete structure is intact above the first floor, but your ground floor has collapsed due to that reason only. And that can be explained with another example which you can see here, that it was intact where we have shown the parking lot, and it completely collapsed due to that reason only. So in retrofit can include installation of a steel frame to limit the deformation of first floor. Another kind of building material, or I should say building material typology, which is there is masonry. that is unreinforced masonry, because masonry is not reinforced. Because masonry is not reinforced, that is why it is called as unreinforced masonry, which is 70 to 80% cases in India is being used. Reinforced masonry has not yet taken place in India right now. It is in very slow stage. So built of heavy masonry walls with no reinforcement, because as you know from since my first slide that force is equal to mass into acceleration, because masonry is having more mass, because the thickness of the walls and all everything is quite huge as far as mass is concerned. So it contributes much to the mass of the building. And the second reason that due to the inherent property of the masonry of not proper connections, since last 70 to 80 years as we are constructing in India, the type of connections we don't have proper in India. Main wall to the cross wall. Main wall means that your shear wall parallel to which your earthquake force is there. That I can say is the main wall, and the cross wall which is exactly at 90 degree to that particular wall. So connection between these two type of walls is not proper in India. That is the reason that one, and the second reason is that your slab is not properly connected to your walls. There is no proper anchorage, there is no proper connectivity in India, and that is the reason that in most of the cases masonry is being damaged in India due to these two main reasons. So due to these we have the out of plane failures, as you can see in the top right corner image, that we have out of plane failure, that is the complete house is intact, vertical elements are intact, but your horizontal elements, which is the walls, they are falling apart, they are falling out, which is called as out of plane damage. Anchorage to floors and roof generally missing. Floors, roofs and internal partitions are usually of wood. So that means that if you are using wood as partitioning elements, and if your structure is not designed properly, the spans you have kept for your slab above for having, then in that case, if you are assuming your wooden partitions to be supporting the structure, that is going, it is not like that, and that is going to increase the span of that particular slab, and you have definitely not checked for deflections. So in that case, the span will increase and your slab will fall in out of plane vertically. Older construction no longer built, typical damage, walls collapse and then roof floors come down. So it could be vice versa also. If your wall falls out, your slab is going to come down, and if there's some problem in your slab, the slab comes out, and if it is having some connectivity with your walls, then your walls are going to come out of plane failure. Parapets fall from roof, which is, if you consider parapet as a non-structural element, they even can be responsible for damage, because a person is walking through on the road and a parapet comes out and discontinues, removes from the top floor, and it comes down, falls on a person or a car which is standing on the ground floor in the parking lot or elsewhere, it could be damaged. The person is going to lose his life. Tilt-up construction, that is again, we have shown here by these figures that what is out of plane failure and what we can take care of, what could be the reason. Because in case of steel structures, as we have shown here, you can have a complete wall of steel which is running from bottom to top. It is a homogeneous wall because it is of structural steel, and it will be a little bit, I should say, more safer in out of plane failure. But this is the type of behavior which we want to have in case of masonry also, and that is the thing which we want to take care of. Mobile homes, factory built dwelling, lightweight. This is also not famous in India. It is being used in Japan and other countries, which I've initially mentioned also. So these are having a typical wooden structure which is light in weight and it can be rectified easily in case of retrofitting. And it can also be, as if it is a mobile home, it can be moved from one place to another to take care of the seismic scenario. But whatever the I should say specifications are there for it, and other things are there that are out of the domain of this particular lecture. Seismic retrofit, that again I will come to it, that we need to take care of either initially for a particular building, or after earthquake we can do the seismic retrofit. In both the cases we require proper design and analysis. There are basically some types of damages we need to analyze, that what kind of damage is there, what type of structure is there, the structure could have what kind of damage. Keeping all those things in mind, we can analyze and design our seismic retrofit. As a precautionary measure we can keep, such as the things we have shown here in this figure, that you can have fluid viscous dampers. As you can see in the this box, the dampers are there, and as soon as we have earthquake, that building moves, these diagonals try to move, the liquid in the damper moves, and it mitigates and dissipates the energy of the earthquake. It is the same as your bike suspensions or bike shockers. They try to mitigate and dissipate the whatever force is being generated by the potholes of the road. So it is same, the thing is same. We have the fluid viscous dampers which try to dissipate and mitigate the energy of earthquake and making the structure safe. That is right now, it is out of the domain of this lecture, but I can tell you that they are depends on various things about the building in which you are using, whether it is steel building, at what story you are using, what type of building is there, what is the analysis giving out the forces. So depending upon keeping all those things in mind, you can design that. That is, you can approach the company which is providing you the damper, that for such and such force I need the damper. Accordingly they will provide you, and accordingly you can apply it depending upon the anchorage what you are going to use. Again, base isolated buildings, as you can see that a building without the base isolation is having less deformation, less displacement, as compared to the building which is having base isolation is having less displacement. So this is the purpose of base isolation, because what it do is it disconnects the superstructure with your soil, or I should say it disconnects your superstructure with the substructure. In case of originally building which are already constructed, we chop off some part of the foundation and we place the rubber bearings in place of that. And in case of being constructed newly buildings, it is very easy. We keep on constructing as we come from foundation level to the superstructure level. We first place the bearings, then we construct the superstructure. But in case of buildings which are already there, in that case we chop off some part of the foundation, and at that place we place the bearings which make the structure in isolation, behave in isolation. And there is also a complete design for that. You need to analyze the forces which are going to come out, and accordingly from whatever company you are taking the bearings, there you can have you can give your configuration, your forces, and accordingly you can place the order, and you can see the even I don't know, it is not much famous in India right now, base isolation, but it is quite famous outside India. They have base isolated huge buildings, as you can see here in the figures, Bay Area base isolated buildings, which is a very huge building, and it is approximately an area of 100 meters to 300 meters. And you can just imagine the hard work or the expertise or the labor what would have been required to base isolate this building. In the middle bottom figure, it has been shown that what is going to be the procedure. They have removed a part of the foundation, and they have first supported the superstructure with some cantilever supporting, vertical structural supporting. Then they have chopped off some part of the foundation, and then they have placed the bearings onto the structure, connected the base isolation bearings structurally with the foundation and the superstructure, and then they have left the structure to vibrate in base isolation, so that the displacement is reduced corresponding to any earthquake, and like that. So there are a couple of structures are being mentioned here. That is U.S. Court of Appeals, San Francisco, survived 1906 earthquake, seismic retrofit in 1994. San Francisco City Hall, steel frame with stone exteriors, seismic retrofit 1994. Non-structural damage, that is equally important. We can't ignore it, because sometimes non-structural damage becomes very heavy to the calamity and the damage of life even. So if you take care of, if you consider nuclear reactors, in case of nuclear reactors, whatever components and machines are being attached to the walls of the nuclear reactors, they are, although they are non-structural, but they are taken care of equally, with equal importance to the structural elements of that particular structure. They are being tested in shake tables in IITs, mostly in IIT Roorkee, and then they are being calibrated, evaluated, and then placed in their nuclear reactors. So there are some non-structural things which we have shown here, library, almirahs, and all those things which are being connected with some angle iron. So we need an analysis prior, I should say, planning for these things also. They can't be ignored. What is earthquake? As we all know, this is simply a ground shaking having a focus which can be a few kilometers to hundred of kilometers down the earth crust, and the energy mitigates and travels the path simultaneously to the surface of the earth, giving the epicenter at the surface of the earth. And this type of ground shaking, we have some acceleration, and this radiates the seismic energy caused most commonly by sudden slip on a fault, volcanic, or any sudden stress change in the earth. That means, as you all know, that the plates are moving on our earth crust, and due to the stress being developed in our earth crust, there is a different types of fault failures which are responsible for this type of things. Internal structure of the earth, which we have different layers. As you know, the topmost is crust, which is responsible for the movement of the I should say layers, which are continental layers, which I am going to show you in my succeeding slides. These are different types of, we have the continental to continental, oceanic to continental, and oceanic to oceanic type of plates which converge, diverge as per their configuration, and depending upon that we have the earthquakes. So continental to continental drift, oceanic to oceanic drift, or oceanic to continental drift, they can be responsible for different type of earthquakes, having different magnitude depending upon the type of plate movement they have. So convergent plate, this is that one type of fault failure, that one plate is going downside, converging with another, and we have a stress developing there, and that stress is being released in the form of earthquake. Energy is being released suddenly, which is being shown again in the right side slide. Divergent plate, which is stress is being accumulated in this form. Earlier it was going down. Now in this case, the two plates, whether it could be continental to continental, oceanic to continental, or oceanic to oceanic, they can be rising both ways, and then in that case they can have an earthquake. Transform fault, it is an across type of thing which there's friction is developing and the two plates are moving side to side. Two plates are moving side to side, and this could also be responsible for an earthquake. These are the tectonic plates which we are talking of. So we have Australian plate, Pacific plate, Eurasia plate, Caribbean plate. So as we all know that ours in an Australian plate, India lies in that. So it is being known by some of the researchers that it is going to range. This Australian plate is moving northwards and somewhere in between the Himalayas with a range of 1 centimeter to 4 centimeter per year. That is the reason that they are converging, and this is the reason that the areas just beside or along this plate length are very much critical. That is why the two major earthquakes, or I should say lots of major earthquakes have happened in the past along this plate only. If you talk of 1905 Kangra earthquake, 1934 Bihar Nepal earthquake, and 1897 Assam earthquake, Bhuj earthquake, all these earthquakes have taken place along this plate belt where the boundary is lying. Types of fault, again which we have shown in our preceding slides, that normal fault, reverse fault. So they are subclassifying it, extension, showing the extension in the way where the shortening is there, where the extension is there, lengthening is there. This diagonal slip also is there, which is called at oblique slip, and the slip which is parallel, which is called as strike slip. Earthquake focus and epicenter, which I've also explained you earlier, that where actually the earthquake has occurred from the point where the energy is being released, that is called as focus, and it travels following a path and comes up to the earth surface, and a point where it comes up to the earth surface, that is called as epicenter, and it definitely comes above to the earth surface on a fault which is already being lying onto the earth surface. They can be detected most of the time. Sometimes they are not being detected, but due to the research and all those things, we know whatever faults are being lying in your Himalayan belt, MBT thrust and all those, the faults we know, and across those faults sometimes whatever, if epicenter is there, we can locate them, that across this fault the epicenter was here. Now the types of waves which are being traveling due to earthquake. We have two types of waves, body waves and surface waves. Body waves have further classification, that is P waves and S waves. Surface waves are two types, Rayleigh waves and Love waves. These are classified depending upon their motion, the whatever we have the path of the whatever constituents are there. We have discretized this particular wave in small elements. So depending upon the type of vibration phenomena of these small elements, discretized elements, they are being classified, that what is going to be the motion of this particular element. It is exactly translation, that means it is P wave, and if it is of different oscillatory type of motion, in that case it is S wave. So depending upon the particle motion, they are being classified as P wave and S wave, which here you can see that it is exactly translation in first case and a bit oscillatory in the second case, which is vertical also. Now Rayleigh wave, here you can say it is a combination of your elliptical thing and translation, depending upon the height from top to bottom. And the fourth one is love wave, which is a different kind of behavior of phenomena of vibration movement as compared to Rayleigh wave, and because Rayleigh wave is completely showing a elliptical path at the top layer. Earthquake size. One thing is intensity of earthquake. Second thing is magnitude of earthquake. Intensity of earthquake means basically means whatever damage is there due to that particular earthquake. At the epicenter, the damage is more. And as we move away from the epicenter, the damage slowly reduces. So we have some scales and some gradings according to that. So that can be calibrated into some, I should say, damage scales. That gives us intensity of an earthquake, whether it is 1, 2, 3, 4, 5. So, and the magnitude of an earthquake is different. Magnitude basically is an amount of energy being released due to that particular earthquake. And that energy can be evaluated using various equations that we follow in while calculating the seismic behavior of the structure and all those things. That using different equations, moment magnitude is there, and other equations are there using which we can finally evaluate what is going to be the magnitude value. This is a modified Mercalli intensity scale. There are prior to this, there were many intensity scales which were being developed internationally, and finally we have come up to this scale that we are going to use it. This is the intensity 1 is insignificant. That is also after many years of research, it has been found that how these intensity scales have been developed, going door to door after every earthquake and finding out from the people that how you felt during that earthquake. From if you are having 4 family persons in a family, and you ask individual to every member, depending upon those recordings, depending upon then you come out and you depending upon those recordings of a colony, then of a city, then of a district, you can prepare those intensity scales. So after lots of research, these intensity scales are being prepared and they are being documented. One of this is modified Mercalli intensity scale, which shows starting from 1, it is an insignificant, in which is only detected by instruments. That means it is not being felt by human beings elsewhere, and it is only being detected by instruments. You might also be knowing that every day there is a earthquake. Lots of earthquakes are there in Himalayan belt of magnitude 3.4, 4, 4.5, which are not being told to a common man, because they are being recorded in the instruments. Very light, only felt by sensitive persons. Oscillation of hanging objects. As you can see, the pendulum is moving. If you are having old type of clock in your home, a pendulum simply vibrates like this a little bit. Your fan starts vibrating slightly, and those type of thing. Light, small vibratory motion. Moderate, felt inside buildings. Noise produced by moving objects such as your cup plate in your kitchen and all those things, which you might recognize or you might not recognize, again depending upon your senses. But they have categorized it here as moderate. So depending upon this, there we have different intensity scales, and what range of magnitude could be there corresponding to those particular intensities. This also has been given in the extreme right column of this slide, which is intensity 1 is 1 to 1.9, and if we come out to intensity 8th and 9th, which is destructive and ruinous, it comes under the magnitude of 6 to 6.9 magnitude. Richter magnitude, that is what I was telling you, that these are some types of magnitudes which are being depicted here, because that is not only a signal way to show the magnitude. There are different equations to find out the magnitude, because there is a different way to evaluate the energy release. Body wave magnitude, which is depicted by MB, surface wave magnitude, which is MS, and moment magnitude, which is MW. These are typical earthquake records, which is being recorded in accelerogram. As soon as earthquake comes, a needle moves on a paper which is being round up. I can show you in my succeeding slides. So this is the type of record which is being recorded, and in this only we make the difference at which is the P wave, which is the S wave, and which is coming initially and laterally, and from that we find out the coda length and then the magnitude. So depending upon the magnitude, ground motion and energy variation can be seen. So whatever, if you are having the magnitude of 1, magnitude of 0.1, 1.3 times is the ground motion change, that is the displacement, and about 1.4 times is the energy change. That is, if the magnitude is changing with a difference of 0.1, it is varying from 6.9 to 7. And if the magnitude is changing by 0.3, the ground motion changes 2 times, but you can see that energy changes 3 times. And if your magnitude is changing by 0.5, that means ground motion changes 3.2 times. It is not that much as compared to your 0.3, but energy change is again huge, which is about 5.5 times. But if your magnitude is changing by a value of 1.0, that means it is coming from 6 to 7, then you can see what is the change in energy release. It is huge. It is around 32 times. So as your magnitude value moves from 1 point ahead, the energy release is increasing 32 times. This is shift of your Australian plate with the Eurasian plate. That means it has been documented that it is moving since hundreds of years back to northwards. Now, since last 50 to 70 years, the seismic evaluation, analysis, and the things have changed rapidly. The people have been able to calibrate and evaluate by research that what is the amount by what amount they are being changing the values. That is why they have seen that 1 centimeter to 4.5 centimeter is an average value by which the Himalayas are rising. That means this plate is shifting northwards. Indian plate is going up, down like this. Movement of plates. Himalayan frontal thrust. That is what I was telling you, that there's a network which is being placed throughout the Himalayas of sensors, which takes the data of the plate movements, and that data is being transferred to the whatever the center is there. As one center is there in IIT Roorkee, which used to be the main center earlier, it can record data from even from China, whatever is there. The distance is no matter. So depending upon that, on the local vibrations, small vibrations, and a small time duration evaluations, we have been able to find out whatever MBT thrust and all those whatever faults we have in India, in Himalayas also. So those are being shown here by lines and of different legends. This is our Indian zoning map, which have shown that we have 4 zones, and they are as shown in the color. That zone 1, which is having the lightest, I should say PGA, or the least PGA, that is least intensity of vulnerability. And then we come to the zone 2, which is a little bit more vulnerable as compared to zone 1, and the extreme one is our zone 5, which is, and zone 4 and zone 5 are thought to be critically vulnerable regions where we should take care of structures critically. Now we will be discussing earthquake effects. What could be the different RCC structural failures? I will be discussing that in brief. As you can see in the figure, that we have a complete collapse. If the building is not properly designed and it has crossed all the limit states, serviceability limit state, occupancy limit state, and it has reached the collapse limit state, that means it is going to collapse. But we can just safeguard them. Pounding and tilting of buildings, it is one of the types. Pounding is a case where we don't have sufficient gap in between the buildings, that is which we require to maintain between two buildings as per the Indian codal provisions. And if you are not maintaining those gaps, then in case of an earthquake, the pounding is going to between these two buildings, and the damage could be more worse if the slab level is in between. The slab level is not the same at the same level of the two buildings. The slab, because the interstory drift at the slab level is different, it is more as compared to your story in between level. So it is going to hit the wall of the other building, and it is going to produce more damage as compared to the other case. Other thing is your tilting of the buildings, that includes your geotechnical investigation. It could be, there could be any reason depending upon whatever was the cause of that failure. Complete tilt of the building due to liquefaction or any other thing, it is going to tilt, subside, and it is going to hit the other building and making the damage to other building also. Staircase failure, which is the first and foremost failure in case of a structure. The reason, because the staircase is a little bit vulnerable structural element in RCC structure as compared to other structural elements. So in case of an earthquake, it behaves as a fuse to your structure. So as we have a problem in our electrical circuit at homes, in that case our electrical fuse is being damaged, safeguarding the other things in our electrical circuit. Same is the case here. In case of a staircase, it got damaged itself, and the reason is that it's, in that case, it saves the building, but we need to have the staircase intact because people have to evacuate out of the building. For that reason, we need staircase first and foremost for the evacuation of the people. So in that case, what we can do, we can just provide staircase structurally independent of the actual RCC structure. We can just completely disconnect this staircase structure with the actual RCC structure, keeping that a little bit of structural connection between the two. Soft or weak story failures, which we have also discussed earlier, that due to the stiffness difference of the immediate floors, due to the stiffness difference of immediate floors above or below, or 2 to 3 floors above the story in concern, that stiffness difference will produce soft story mechanism into the building, and the building concerned will be having soft story failure in that particular story. Suppose you leave a duct or a floor which is 1 to 1.5 meter high for ACs or for maintenance or for something, and you think that it is not of much of importance, and you give the less cross section to your columns and anything else. In that case, that story or that part of your structure is having very much less stiffness as compared to your upper and below floors. In that case, you will be having soft story failures. The same is being depicted in the figures as being shown here. That is 2001 Bhuj earthquake figure, which is a complete one story, which is ground story has collapsed, And it could not be the case only with the ground floor. It could be a case with intermediate story also. As I've explained you just now, that it could be an intermediate story also. Whatever the story which is going to have a stiffness less as compared to the floors above and below, which is 70% to 80% variation is there, it is definitely going to be damaged, and a complete collapse of that particular story is also possible. Ground rupture is one of the, I should say, destructions, failures of an earthquake. As you can see, such a huge ground ruptures are there, which could be further responsible for another indirect possible failures of roads and lifelines. Slope failure, wherever we have shear strength less, or the homogeneity of the soil is in consideration, or it is vulnerable, then we can have slope failures. Liquefaction of soil, as we all know that shear strength of the soil is the major concern and criteria to evaluate the soil conditions. For earthquake, as the motion is vibratory motion, to and fro motion, in that case, the soil loses its shear strength because of the to and fro motion, which can be evaluated. Shear strength can be evaluated at lab level or in situ level by various ways. Using those ways, we can evaluate the shear wave velocity of the soil where the structure is supposed to be constructed. And based on those shear wave velocities, and indirectly the shear strength of that particular soil in that region, we should evaluate, and then only we should construct our structures depending upon whatever strength we are having, whatever bearing capacity we are having of the soil. So liquefaction is a phenomena where the soil loses its shear strength completely, and we have a quicksand type of condition where the buildings start floating slowly and they tilt completely in that case later on. Lifeline structures are important because in case of an emergency of an earthquake, we have to maintain the connectivity, we have to maintain other life-saving situations such as hospitals and telephones, connectivities, electricity, because if they are going to fail, in that case the situation is going to become more critical. We won't be able to save more lives because we need road connectivity and all to take the people to a safer place and to hospitals. So these are of equal importance and they are required to be safeguarded, and we require the measures to be taken for them of structural safety. As you can see in this figure that we have, you can see the bottom left corner figure where it has been shown that a masonry structure is standing, whereas the RCC structure on the bottom right corner is failure. The reason being, on the left bottom left corner, the masonry structure is having bands provided. Are we okay? That means this figure shows that as we can have slow failures. If there's little bit of a number is less of the houses, then the damage to life is going to be less. But if we are having this type of construction, in the case of slow failure, then one above the other and one another, the next to other, the houses are going to be pounding each other and falling on each other, and in that case the damage to life and property is going to be heavier. So this is the scenario in hilly regions right now, but we need to just rectify and change the things as soon as possible. Next is I'm coming locally to the things which we need to take care of. That is why the title of the topic of this seminar is that what we need to design, what are the things we need to keep in mind while designing the buildings. Few we have discussed and the few we are yet to discuss. That one is the thing that, as you can see in the figure, that it is plinth level beams are there. The connectivity of plinth level beams, as we know, there should be shear is the main thing in case of an earthquake, whether it is for structural elements, whether it is for horizontal elements. It has to be taken care of very well. Now you can see in this figure a plinth beam is connecting to another beam very close to the column beam connection. If you consider that this beam and the distance between this beam connecting the another plane beam and the beam column joint, the difference between the two is very less. So this distance is very less and is going to increase the shear forces in this particular part. But your plinth beam is not being designed for that type of increase in shear forces. So definitely this part is going to have shear failure. Hinging is going to form in this this portion, and you will having a complete failure. Initially this part will fail, then a complete beam will fail, and then your structure at the start of the columns will be having hinging, and then your structure is going to slowly collapse. So this we need to take care of, that these things should not be done. We have to have the proper planning, management and configuration of every structural elements, whether it is vertical or it is horizontal. This is the basic thing, that how the earthquake acts and how the load is being transferred. How is it acting and in what direction it is being transferred, that it is acting in one direction, and as we have the rigid diaphragm, or you can say as we have slab above our vertical elements, it is going to, as we say in bus, when we travel in bus, as soon as the bus starts, our body moves back as our legs are in motion with the floor of the bus. So this is the same case with this figure, that your ground starts moving but your slab is at rest. So the motion of slab and your ground level is different, and that is directly proportional to the inertia force being developed due to the slab mass, and a half mass above floor slab level and half below slab level. So this is the way that how it is going to move and going to develop the inertia force, which is going to generated due to the mass of that particular floor or building. And the same is the case for RCC structures. We have this type of displacement profile of columns and slab, and along with the motion of the ground, they both are out of phase at the slab level. By this figure, we are showing what is the effect of torsion. Keeping the mass and stiffness conditions at balanced level, we are required to keep mass of a building very well distributed and stiffness as well, because both are equally important. If you are increasing the size of the columns on one side of a building, which is very huge in length, in that case mass as well as stiffness is increasing on one side of the building, and it is going to have the torsion due to the motion. And as we have shown here with the figure, that the girl is, as soon as girl shifts its place from center to one side of your swing, then the motion becomes translation. It changes its position from translation motion to torsional motion. But if girl continues to sit in the center of the swing, it going to be translating in the translation motion. And if you can see here that there is a change of stiffness of the ropes, that the length has been changed of the swing. So you have a more slender rope which is connecting on the right side of the swing, along which is bringing change in the motion. That is the same case with the buildings which are being structurally connected on built on the hilly slopes. In that case, what we have short columns as we go up the slopes, and we have slender columns as we move down. The length is more, and which makes the building slender on the later part. And you have the torsional kind of motion which is vibrating in a rotation. This is the kind of rotation we have, and due to this reason, what becomes that the column forces becomes critical. This type of rotation motion, what we do, we have to design your columns critically for that type of forces we are going to be developing in that case for the torsional motion. So we need to avoid these type of conditions as far as possible. If you can't avoid, if you are doing it, you are constructing it, then you have to design it accordingly as per the Indian codal provisions and whatever actual by analysis you are getting the forces, keeping all the boundary conditions and specifications into consideration. Important parameter of building during earthquake. Buildings with higher natural frequency and a short natural period. That means short structures. That could be of RCC as well as masonry. Suffer higher accelerations but smaller displacements. That is the reason that they come into the stage of destruction very close, very fast, because they have smaller displacements and they complete the cycles very fast. They have high frequency content. Buildings with lower natural frequencies have a longer natural period. Definitely that is the case with the multi-story buildings. Experience lower accelerations but larger displacements. So in that case, if your building is not being designed in a ductile manner, which is not allowing your building to have large displacement, in that case, there could be a damage in that building. So if you are designing for large displacements in your multi-story buildings, it is good and it is going to safeguard your building for those extra forces. Height of a building is related to another important structural characteristics, the building flexibility and stiffness. Flexibility and stiffness are really just the two sides of the same coin. That is, ductility is the ability to undergo distortion or deformation, bending, for example, without resulting in complete breakage or failure. That means if you are designing your building for more displacement, that means you are using your building to the maximum ductile performance. You are allowing more displacement with less forces, with less damage. That is the use of using ductile materials as per Indian standard 13920 code, Indian code, just for the ductile behavior of reinforced concrete structures. It is far more desirable for a building to sustain a limited amount of deformation than for it to suffer a complete breakage failure. Ductility of a structure is in fact one of the most important factors affecting its earthquake performance. Damping in a building. Damping is an intrinsic property of any material, and constituting that intrinsic property in a building, when earthquake comes, that thing directly, indirectly, in many ways contribute towards the damping phenomena of a structure, as it dissipates and mitigates the energy of an earthquake from top to bottom. It could be friction due to the material. It could be your vibratory motion of different structural elements, and all those things combinedly constitute the damping of a structure. So that damping comes up and it mitigates and dissipates the energy slowly, and your structure comes to rest finally. So this is a coefficient, this is a constant which is connected to every type of material. Steel is having different damping, masonry is having different damping, and your RCC is having different damping. The decay of amplitude of a building's vibration is due to internal friction and the absorption of energy by the building structure and non-structural elements. All buildings possess some interesting damping. The more damping a building possesses, the sooner it will stop vibrating, which of course is highly desirable from the standpoint of earthquake performance. Earthquake resistant design philosophy. We need to follow a design philosophy because we need to calculate the earthquake loads, and depending upon what kind of service we require from the structure, and it indirectly depends upon what is the type of structure, whether it is a hospital building, whether it is a nuclear reactor, or whether it is just a storage structure where the material is being dumped. Of course, it is going to be having less importance as compared to your hospital or nuclear reactor. So in that case, we need to evaluate and calculate the earthquake load depending upon the serviceability limit state, damage limit state, or collapse limit state. So at what stage, till what stage we can allow the structure to deform and have your damage pattern. So you can see here that minor shaking is going to contribute just a little bit of small cracks. Moderate shaking is going to aggravate and increase the value of cracks and the cracking pattern. As you can say, the hinging is initiated at the beam level. It is at the 3 points. In minor shaking, there is no hinging. There is nothing in red color in the beams. And as you move on to the strong shaking part, you can see that hinging is there in all the 6 parts from the front elevation, and the cracking has increased and aggravated, and the structure is just about to collapse. So as we move on from serviceability limit state, damage limit state, and collapse limit state, we are allowing the structure to deform more, have more cracks, and that is you are going to design, you are going to decide that what is your requirement as per the limit states you require. Seismic design principle as per IS 1893-2002 are the design basis earthquake, which is expected to occur at least once in the design life of a structure. The maximum considered earthquake MCE is the most severe earthquake effects considered by IS 1893. See, as it is clear that this is design basis earthquake and it is considered at least once in the design life of a structure, and MC is the most severe earthquake. That means from DBE to MC, the forces, the load is increasing. Usually only DBE is considered for design of structures, but MCE can also be considered in case of very critical structures, or depending upon the situation for what you are designing. If you are designing for a heritage structure or if you are designing for a nuclear reactor, again the things become critical and various parameters are considered. Keeping that into mind, you can decide whether you are going to consider MCE or DBE. Seismic design philosophy, the design philosophy adopted in the code is to ensure that structure possesses at least a minimum strength too. So there are these 3 criteria. Amongst these 3, you can decide that what is your requirement, that whether you want minor damage, whether you want moderate damage, or you can allow the structure to collapse. So with resist minor earthquakes less than dB, without damage, which may occur frequently. That means the earthquake is occurring frequently, but you are allowing that much damage. Resist moderate earthquake without significant structural damages, to some non-structural damages may occur. So you are allowing some of the non-structural damages may occur, but you are not allowing the structural damage to occur and withstand a major earthquake without collapse. That means you are allowing structural damage at a more aggravated and increased level as compared to this level 2, but you are not allowing the structure to collapse. You are giving time to people to evacuate from that particular building. This is seismic hazard and microzonation of area, which I can just is going to give you a brief about it, because it is a more specific field of earthquake research. That is, we put sensors locally. One is that we put sensors all throughout the country and at a distances more. In my seismic microzonation of area, that means if you are putting sensors at a smaller area, that means if you are putting sensor within the city of Chandigarh, across different places around the length and breadth of the city, to just find out where are the local faults are there, so that you can plan the pipeline of the city. You can plan the lifeline things of the building, that is your telephone line, your electricity line, all those things you can plan as per your planning thing. Depending upon that, you can use the sensors, and depending upon that data, once we club those data, and just we can give the microzonation of that area. Utility of microzonation maps. That at what places microzonation can come up and can serve us. Planning and placement of essential services. That is, as I told you, plumbing, your sewer line, your electricity line, your telephone line, your bus routes, everything can be planned, designed, changed, shifted according to your microzonation. If it is not being already planned, if it is already the things are designed and planned, then you can just change them. Design and construct the structures properly according to the information provided by the maps. Whatever the person who has done the microzonation of that particular area, he or she is going to give you the maps, and accordingly you can plan. Strengthening of existing structure and buildings. That means you have just located that there is a fault nearby to a structure. So in case of a future recent earthquake, you can just plan that there is going to be if there is going to be an earthquake, we can have a damage critical due to this particular local fault. This is the vulnerability status in India, because 70% of the building stock is masonry, and moreover, which is not being designed in India. We don't use design buildings, whether it is masonry and RCC, and the scenario is more gruesome in case of masonry structures, which is of course 70% of the building stock. So Ministry of Urban Development denotes that about 65% of the land area of India is vulnerable to seismic damage, although this data is around a few years back. The vulnerability is increasing to about 50% from 25.7 from 1991 to 2025. This is particular to a typical city, which is Dehradun city, located on Indian map. This is the congestion you can see, and moreover the building stock, there is a different typology. When we evaluate the vulnerability analysis of a particular city, we consider that what type of buildings are there. The building stock should be whether it is having the same type of buildings or it is having different type of typologies. This is the zone 3, zone 4, zone 5, whatever in zones they are lying, and what is the critical status of these particular cities in that particular zones. So they are hugely vulnerable. Zone 5 is Guwahati and Srinagar, although they are in zone 5, and depending upon the building stock, typologies and vulnerability status, they are hugely vulnerable. Typically, majority of the constructions in these cities are not earthquake resistant. Thus, an earthquake striking in one of these cities would turn into a major disaster. That is the reality, because only one earthquake, that is the Bhuj earthquake, which has struck India close to a city which is densely populated. Otherwise, we don't till now yet have any earthquake which is very close to a city which is densely populated. The scenario is very gruesome right now, and is going to have critically damaged. We will be having cities if it is going to continue. This is the same slide which is showing that flow of seismic inertia forces through all structural components, how they are going to behave. Then generating force, as you can see here, that force is increasing downwards. That is, whatever shear is accumulating due to the earthquake force. It is, if we talk of energy, it is quite high at the top level, but if we talk of force, it accumulates from top to bottom. At the top floor, whatever is going to be the forces, they are going to add on to your floor level, which is just beneath that, and then they are going to just add upon, and they are going to increase downward. Floor level, slab, and this is the transfer level, how they are going to transferring the loads, because diaphragm level, which is floor level, it is the first one to have the assuming or which is having the earthquake force, and that it is going to transfer it to the beams, and the beams are going to transfer it to the columns in case of RCC structures, and to the walls in case of masonry structures, and they are going to transfer that to the foundation of RCC as well as masonry structures, and they are going to accumulate from top to bottom and increase. That is why we have the maximum shear force in the ground floor level for which we need to design our ground floor levels critically. Again, if we talk of this type of energy transfer and your translation motion, that we need to keep the configuration of the buildings very much planned. You need to keep the stiffness same throughout the building. You can't increase or decrease the stiffness abruptly. Same is the case with the mass. You can't increase or decrease the mass abruptly. You have to keep a consistency from the foundation level to the top floor level. If you are providing a particular stiffness, or you are providing a slab thickness and your column sizes, that you have to keep a consistency should be there from top to bottom. Single story building, 3-story building, we have a translation motion. We have kept the things quite same from top to bottom. Although, as you can see, the one with the having long strings will be having large displacement and large time period and low frequency, as compared to the one, a multi-story, which is having 1 degree of freedom and 3 floor levels. Now, if you are going to change it again, which we have shown here, we have shown that there is heavy mass of a building on one side. So due to that heavy mass, there will be a torsional movement on one side. The same is the case with the change in stiffness of the columns. Slender columns are going to impregnate a rotary motion to the structure at the bottom level, and that is going to make the columns critical on the lower side. And in that case, to the corner columns. The corner columns are going to be more affected as compared to the interior columns, because they are supposed to transfer the forces to the columns in that parallel line. This is going to be the site selection. These are the things, some of the things which we need to take care of. What are the things which we need to keep in mind during the site selection you are doing for your building to be constructed? That your building should be sufficiently away from the slope, steep slope. First you have to make sure that you are not making it close to steep slope. And if you are trying to keep it close to the steep slope, then in that case you should be based on piles, and that too should be designed properly. Foundations. Structure shall not be founded on loose soils. There is a map in Indian codes also giving the discretization and classification of the soil conditions throughout India. So there's a classification, you can follow that, and you can have your own geotechnical investigation for that particular area where you are supposed to construct that particular building. So they are not supposed to be on the loose soils, soft silts, expensive clays, because in that case what is going to happen, depending upon the IS code, soft, medium, rock, the forces are going to increase and the structure could be damaging. Proper soil investigation definitely is required. Building should be founded on same type of subgrade. So in this case, if you are having shear wave velocity, you are having in situ bearing capacity, whatever method you use, you should just finally evaluate and calibrate that the area till few meters, it should be consisting of the same subgrade. There should not be much of a variation in your subgrade in terms of parameters such as shear wave velocity or the shear strength of the soil, whatever you want to keep it. In case of variation, separation joints should be provided. That means if you are having two buildings, different buildings having different subgrade, accordingly you can separate the two buildings and you can do the geotechnical investigation analysis for the two buildings separately. And accordingly you can plan, analyze and keep the forces for those two different buildings and keep the structural elements accordingly. loose fine sand, soft shells, expensive clays. For these type of clays and soil conditions, you are supposed to provide raft or pile foundations, which are going to give the common type of displacement to your foundation level. Isolated footings for columns. Provide tie beams perpendicular to each other. That is definitely in case of you are using raft foundation or any type of foundation. If you are using tie beams, that is going to reduce your differential settlement at the bottom. It is going to confine the building to maximum level. It is going to dissipate the energy to a more larger area equally. That is the reason that we provide tie beams. If you are not providing tie beams, in that case, one of your footings or foundation is going to subside more as compared to your other footings or foundation. Minimum depth of foundation. Plinth band is not required for foundation on rock and hard soil, but it is required other than that. So there are the specifications that you are supposed to follow as per Indian standard codal provisions. You could have told me earlier also. Foundation in soft soil, foundation on rock. So it is not required, but as compared to other than rock, you are supposed to provide the plinth band. Foundation in liquefiable soils, strip footings sink due to liquefaction. So you are supposed to consider all these things. If the strata is like liquefiable soils, you are supposed to keep the pile foundation in that case, and it is always suggestible to use raft foundation because it gives the same type of displacement to your superstructure. So there is no difference in displacement to your foundation level through the length and breadth of the building. IS code for designing the foundations. IS 1080-1989, design and construction of simple spread foundation. 1904 shallow foundations, 2950 raft foundations, and 2911 part 1, 2 and 3 on pile foundations. Now we come on to the good and bad of different materials. As you can see, masonry is good in compression, but masonry is weak in tension. That is the reason that because earthquake phenomena imparts to the structure more tension, because most RCC as well as masonry is quite safe in compression, and both plain concrete is and as well as masonry is vulnerable towards tension. So this thing is very critical to be taken care of, that while designing what type of material we are using for what type of structures at what level. Ductile versus brittle materials. That is for sure, we always require ductile materials as compared to brittle materials, because brittle materials don't give us more of a time to evacuate or safeguard our structures. So we require ductile materials for the safe design of the buildings for all limit states as well as for final limit states, that is collapse limit states, so that we can have the more displacement as compared to brittle materials. Steel is ductile, concrete and masonry are brittle, so we require steel. And if we are using steel in RCC, that means plain concrete, that is going to give us RCC, which is again a ductile material. Walls behavior during earthquakes. That is, as I have talked of it earlier, that in masonry, the basic problem is, one is that masonry is a brittle material, and the problem becomes more critical due to the reason that we don't have the proper connection, despite the fact that we have a brittle material in consideration for construction. But if even if we are using masonry, if we provide proper connections to our structural elements, whether it is parallel to the earthquake force and perpendicular to the earthquake force, and with the horizontal diaphragm level. So if we are having connections in plane to with the cross wall and your both the walls with the slab, if we are providing those connections properly, in that case, that means we are safeguarding our masonry structure for a future collapse due to earthquake. So as you can see here, as it has been shown, that a wall is there in which the earthquake load is acting perpendicular to it. So as we calculate moment of inertia BD cube by 12. So in that case, inertia, if you calculate which will be maximum, it is going to increase if you are in plane. The wall, the earthquake force is acting parallel to the more length of the building. So in that case, it is going to act as shear wall, and it is going to safeguard the building more. And in the other case, the inertia will be less, and due to that reason, there will be a problem of out of plane failure. The resistance of the wall will be less for that particular earthquake force. So direction of force on a wall critically determines its earthquake performance. That is the reason. So that is the thing which we require to maintain cross wall, main wall to cross wall connection, and your wall to wall connection with the slab. Unless until that anchoring, that connection is not there, there is definitely going to be a future earthquake which is going to let your building be collapsing. So if that is your wish and that is your method, how you are going to maintain that connectivity with your walls, wall to cross wall and your wall to slab. Here they have shown the two figures in which one is not being connected properly, where you can have a roof collapse, and the one which is properly connected, which is going to be maintaining as displacement of diaphragm level as well as with walls along with each other. So that action, that phenomena we can have when we are using bands. If you are using bands, they are going to provide connectivity to your walls, wall to wall, wall to cross wall, and your wall to slab, and your piers to the spandrel. So it has shown here that how these bands can be connecting, making your a masonry box like structure. If you're not providing it your masonry structure, which is although a 4 wall type structure, it is not going to behave as a box like structure. So you, to maintain the connectivity and to make your structure behave as a box like structure, you are required to have a connectivity using bands or stitches or reinforcement. You can use horizontally as well as vertically. Region of force transfer in masonry buildings, as it can be shown from this figure, that as also I have explained earlier, that parallel to your wall, the length of the wall, that is the main two walls corresponding to this figure will be the shear walls, and the other two will be the cross walls, in which a proportion of that particular force, that shear, is going to be transferred to those cross walls. So main two load carrying structural elements will be the walls, which will be parallel to that earthquake force. So it is going to be transferred like that as it is shown in this figure. Brick masonry walls, story construction, 1 story, 2 or 3 story, 1 brick wall. These are some of the specifications which are being given as per the Indian codal provisions, which you need to keep into mind. If it is slender structure and how many stories you are planning, accordingly you can provide the thickness and plan the thickness of your building. And because that is going to definitely, first you are going to analyze and then you can do the things. This is the mortar quality, and these all are minimum thickness is equal to less than 1/16th length of the wall between two consecutive perpendicular walls. Mortar quality lime is to sand. If you are using this type of configuration, that means two consecutive walls, main wall that is parallel to the earthquake force and your perpendicular wall, in that case lime is to sand is equal to 1:3, and the cement is to sand is equal to 1:6 you can use. Stone masonry walls, wall thickness T should not be less than 450 mm, most preferably 350 mm. Stones should be properly interlocked. That is the reason that which we have been discussing since last few minutes, that we need to properly make the connectivity. That depends upon you as per the domains of Indian codal provisions, what you are going to use. Whether you are going to use ties, steel ties, stones, whatever you are going to use, you are just supposed to maintain the connectivity in between the wall and in between the structural elements as well. This is the kind of failure which you can have in case you are not maintaining the proper connectivity in the structural elements in the form of walls, and if you are not providing it in terms of the structural element to structural element connectivity. There is no connection between the two ties. There is no ties of the wall. That is why the wall has fallen in out of plane failure. Provision of through or bronze stones. These are the specifications which we have discussed earlier, that equal to wall thickness. Every 600 mm lifts, not more than 1.2 meter apart. This is vertically what they are suggesting as per the codal provisions. Steel bars 8 to 10 mm S or hook length. Wooden or concrete bars also used. So that is what I am saying, that you can make your own connection lengths. It is not necessary that you are using market. You can use your own, but you have to make sure that they are structurally connected to your structural elements. This is the type of thing which they are going to impregnate into the structure, homogeneity to the structure. Although it is heterogeneous, masonry is a heterogeneous type of material, but you are bringing some type of connectivity using these through stones. These are all the specifications as per the codal provisions. 1200 mm is the in-between distance and spacings, and 1200 mm for the cross wall. You can use lengths also, that could be wooden also, and or whatever material which is compatible with that particular type of masonry. Provision of buttresses, that means you are reducing the span of the wall. It could be horizontal span also, it could be vertical span also. Using the buttresses, you are reducing the span, because in case your span is increasing, the forces are going to increase. And as soon as you are introducing a buttress to a wall, you are reducing the span. That means you are reducing the forces. Basically what we do in beam design, that is WL square by 8 gives you the moment for a beam design. In that, L is the span. You are reducing the L, that means you are reducing the moment, and indirectly you are reducing the forces for you to design. Openings and bearing walls, as I have discussed earlier, that moment of inertia which we have calculated earlier, that is for a force which is parallel to a wall, which is serving as a shear wall, and which is mainly responsible for taking the earthquake load in that particular direction. That is I is equal to BD cube by 12. But that particular slot which is cutting due to a window in that particular wall, that part you are going to deduct from that moment of inertia, which is serving you and increasing the resistance of the building for that particular direction. As we calculate moment of inertia for our I section, all civil engineering students might have done that. We reduce the part which is outside, the flanges. That is the same thing that we reduce the moment of inertia here. And what is the net moment of inertia we are having, that we use as a resistance towards the earthquake. So if we are giving the more openings to a structure, to a building, that means we are reducing the resistance of that building. So you are supposed to keep all the things into the consideration according to the Indian standard codal provisions. Some are given in Indian standard 4326, in which the specifications are being given that you are supposed to keep such and such distance from the extreme right side wall, or from door to window, or from lintel level, such and such things are given. Effects due to large opening, reduce lateral load resistance, cracking in diagonal direction. That is what I have explained, that as you are going to increase the size of the openings, your shear resistance is reducing. Your wall is becoming more vulnerable towards a load, which is in plane to that particular earthquake. What can we do? Small and more centrally located, definitely keeping the appropriate amount of size of your door and window, which serves your purpose, that you are definitely going to keep. Strengthened with 2 HSD 8 bars. This is the specifications which they have given of the steel lines which you can provide around the corner openings. These are the specifications which I was talking about. Indian Standard 4326. That from the door to window, what is the distance you can keep, which makes your building safe towards earthquake, which is not developing critical shears into that part of the pier, which is not making the that particular pier vulnerable towards cross cracking. It is safeguarding if you maintain these distances. A distance of a ventilator to window, your roof slab to ventilator, and your corner to your door to window distances. This is again the distances as compared to B1 plus B2 plus B3 less than L, whatever specifications are given, you can use as per Indian Standard Codal provisions. Band in masonry buildings. Two types of bands, horizontal as well as vertical. Horizontal bands are being shown in these figures. We provide at lintel level, sill level, and roof level. So whatever the band which is comprised of concrete as well as steel all around the building, that is a band which with a specification of reinforcement in that. If you provide it at lintel level, that is lintel band. If you provide it at floor level, that is floor band, and truss to roof level, that is truss to wall connection, that is roof band, which mainly safeguards your structure against your gable wall failure. Gable is this yellow part which is being shown here in gable roof connection, because in most of the old structures, heritage structures, churches, mosques, and your old structures in India, outside India, Europe, there are double to 3-story structures in which the wall is running from bottom to top throughout, with the least or no connection of slab at the floor level. So in that case, what happens? We have a cracking throughout the wall, which is running from bottom to top, or we have a gable wall failure, out of plane failure of the gable part only, which is not properly connected with the rest of the wall which is underneath it, and it is not having even proper connection with the trusses or the perpendicular wall as it is being shown here. So this figure shows a clear indication how simple providing a band can safeguard your building. A person who might have constructed this building, which is in bottom right corner, might not have evaluated or analyzed this building prior to providing a band into it, because it is very old, Kilari, no damage. That is, the simply providing a band, this building has been saved. And for a particular same type close to this structure, we have another structure which was not being provided with the band, and it is completely damaged. So it gives a confinement to your structure, and your structure behaves like a box-like structure which mitigates and dissipates your energy using all structural elements, whether they are horizontal or vertical structural elements. Design of lintel bands. This is simply as you design your simply supported beams using that WL square by 8. You can design depending upon what type of building you are having, what type of boundary conditions you are having. As you can see here, it is a simple 4 walls on which the lintel is setting. But if you are having a structure which is continuous in nature, then in that case also you can design your lintel as a continuous beam having a load which is falling from up. That is, in that way you can design. But there are some specifications also from the Indian codal provisions which I am going to read out here. Grade not linear than M15. Band should full width of wall. That means your lintel band should body throughout the full width. It should not be less than, if you are providing 230 mm, it should not be less than 230 mm because in that case it loses its purpose. Depth not less than 75 mm. Depth you are going to provide for 75 mm. Reinforced with 2 HSD bars. 10 mm with 8 mm bar ties and preferably 150 mm apart. 10 mm with 8 mm bars ties. Wooden bands, uniform section. Again, uniform section is required if you are providing wooden bands. So this is the configuration as how we provide the bands in our masonry walls. Minimum is this, you are providing one link and 2 bars horizontally with the depth of 75 mm. In another case, you are providing again 150 mm double depth and 4 links, 2 horizontally, 2 up and 2 down, depending upon the forces you are going to get in case of your earthquake force. This is the cross section which is given by Indian codal provisions, and a table is also being followed for that which is given in the Indian code, which varies according to the category of the building, type of building. Accordingly, you can design your lintel just by following those specifications. Number of bars, thickness of the bars, dia of the bars, and the spacing of the tie bars. In case you are providing wooden bands, RC bands, this is the right configuration which we have here. They have shown. Incorrect practice they have shown also, because the incorrect practice, it is not at the corner junction, it is not confining the corner using the reinforcement. That is why it has been shown that it is an incorrect practice. You are required to anchor and confine the corner, because corner is the most critical and vulnerable part of the structure. In case, and this is the purpose for which we are providing the bands, to confine the structure. Vertical reinforcement in masonry buildings. We have discussed horizontal bands also, and along with horizontal bands, you can use vertical reinforcement also. So how can we provide the vertical reinforcement? First, let me discuss what are the different levels. So below the window level, the soffit of the window, we call it as sill masonry. And between that lintel level and your sill level, the top of the sill level, we call it as wall pier masonry. That is, piers are there, and that is above lintel level, that is above window and door, because window and door share the same level. We have the spandrel masonry. So lintel level, sill level is given, where we provide the lintel band and the sill band, and plinth band also we provide, as we have shown in our preceding slides. No vertical reinforcement. You can see how the buildings are going to behave. In case we are not providing vertical reinforcement, they are having individual piers are having rocking behavior, diagonal cracking behavior, depending upon as the forces of earthquake are going to increase. The behavior is going to be different depending upon the particular individual capacity of those piers. All the piers have their own capacity, and depending upon that, they are going to resist that particular earthquake force, and depending upon that only they are going to give the cracking pattern or the damage pattern, whether they are going to have rocking, whether they are going to have sliding, or they are going to have diagonal cracking. So for that purpose, we provide the bands all through the building at different levels to confine the building and safeguard the building against these damages of piers, of bottom masonry, of spandrel and all. These all can be safeguarded against earthquake forces if we are going to use horizontal bands along with our vertical reinforced masonry. So vertical reinforcement which is being provided here is shown in the figure. We can simply provide this vertical reinforcement using hollow block masonry, where a slot is there in the masonry through which this vertical reinforcement pass, and we just confine this masonry, these reinforcement bars with the epoxy or simply with the cement slurry or with the cement paste or cement sand constituents. This again is a topic which depends upon various things, various parameters, that what level of design you are doing. But you can definitely provide a vertical reinforcement and to safeguard your buildings along with horizontal bands. So this is going to give you the more ductile behavior of the piers for the opposite direction motion, as we can see here. Corner reinforcement around openings. You can see, as I have told you earlier also, that masonry is strong in compression and weak in tension. So whatever we can see here, whatever portion is weak in tension here, you can see that whatever portion is compressing, that is not having any crack, but whatever portion is having tension, whatever fibers are elongating. If you draw a free body diagram of this window only, you will find that this part where the cracking is shown is having tension. Fibers are opening up here. That is why they are tension, and that is why there is a cracking. So to safeguard this pattern, what we need, we can do vertical as well as horizontal reinforcement being provided in the building along all throughout the periphery of this window in the form of bands, or you can provide horizontal reinforcement as well as vertical reinforcement, or you can provide the bands in the horizontal position and the vertical reinforcement in the vertical position. Frame structures, we have frame construction, space frame, moment resisting frame, vertical load carrying frame constructions, moment resistant frame with shear walls. This category is based upon that how you are designing your buildings, that what part of your building is contributing in resistance towards the earthquake load. If you are designing a frame structure along with a shear wall, so what proportion of the lateral load you are contributing towards the resistance of frame structure and towards the resistance of your shear wall? What is the proportion which you are allocating to the shear wall, and what is the proportion that you are allocating to the frame structure? Box type construction, prefab, that is prefab RCC, in which we do the connections of a fabricated RCC components. In situ masonry and concrete or RCC walls. Reinforced concrete buildings, main materials concrete, sand, aggregate, cement, that's steel bars, that is reinforcing bars. RC building is made of horizontal members, that is beams and slabs, and vertical members, that is columns and again slabs. Rigid diaphragm action. This is how we assume that what kind, there are two things, what actually is the behavior, and the second thing is what we assume the behavior to be in our manual calculations while we develop the stiffness matrix or flexible matrices of a structure. Actually, we assume the diaphragm or the slab level to be completely rigid. So this type of displacement profile is there, as it is being shown at the bottom right corner. This is the in-plane movement, complete in-plane movement, where we see that all the displacement at all the column levels at the same level are having the same displacement profile. That is, the displacement is same. So, and for out of plane movement, we assume that there is a little bit of flexibility in the slab. Accordingly, we develop the flexibility and stiffness matrices, and accordingly we find out the forces. One more thing is there, in case of the RCC as well as masonry type of structures. In case of rigid diaphragm action, that is, as we have shown here in the bottom right corner, we divide the forces, lateral forces, according to the stiffness of the frames or the components. Depending upon that, we define the lateral force depending upon the stiffness, and we divide them amongst the different components and different frames, and accordingly we analyze those frames for the forces, and accordingly we design. But in case of a flexible diaphragm, we assume that they are being contributing whatever the load is coming from up according to the tributary area, and accordingly we just distribute that load to the column and then column to the foundation. Infill wall movement during earthquakes. This is very important parameter that most of us ignore while modeling the structures in our computer softwares and even calculating manually. That is, we are actually, the brick masonry infill is there into the structure when it is in situ casted. But while analyzing that same structure into the computer software, we don't consider that brick infill in our analysis. But the reason is that if you are not considering that stiffness, but actually that stiffness is there, it is actually contributing something to the actual movement and behavior of that particular structure. Quick. But in computer modeling and software analysis, you are not putting that break infill, not considering that break infill. That is definitely going to reduce the resistance level, and that is going to play with the global resistance of that particular building. So you are required to keep the brick infill into the consideration while you model it into computer software modeling of the building. And when you are putting it, definitely the forces are going to come accordingly into your columns, and the reinforcement and the things are going to change. So this is how that simply a gravity load and simply an earthquake load is we have the different behavior of columns moment we are having, and that is the reason that this shows that how can we provide the confining reinforcement. Okay, although the no shear zone and the maximum moment zone are same, but the things are more critical in case of earthquake. Strong column and weak beams. That is that what type of damage behavior or what type of damage we want our building to behave in. That is for sure we don't want our building to collapse. So in that case, what we can allow the weak beams, that is, we can allow the beams to have some type of structural damage. In that case, that the forces or energy is not being transferred to the columns, so that our columns are safe and we can let our buildings to be damaged. That is why what we do, according to the design philosophy, we do some type of ductile detailing so that we allow the beams to let being damaged and keeping our columns to be safe. Otherwise, vice versa, as being shown in the right side figure, if we are allowing our columns to be hinging during an earthquake at the critical zones just above and bottom the beam column joint, in that case, complete structure is going to collapse in a single go, and that we can't allow in case of a earthquake scenario, because we require time to evacuate people, we want to save people. That is the reason we allow weak beam and strong column philosophy. So weak beams just serve as ductile links. They allow the structure to have more displacement, give more time for the things to mitigate and dissipate, and that is why they save the structure, and that is why we can do. If we are going to do the things as it is in bottom right corner, that is, we are making the beams extra stiff. In that case, our column will be weak and they are going to fall apart sooner as compared to beams, and in that case the structure is going to fall apart very soon. So there are some of the specifications we require to keep the things in control. There are small things that we are required to keep this hook where we are providing confining reinforcement. We are required to put it at 135 degree, not at 90 degree. That is 135 degree. If you calculate, you draw a line parallel to your length, and you calculate 90 plus 45 is 135 degree, and they should be rounded inside, and they should not be left over along to the tie, exactly at 90 degree. Two types of damages in beams that we are seeing here, that shear compression failure, which is inclined crack at 45 degree, and flexural failure. How to design beams, this is important. That as I'm talking of since many preceding slides, that we need to keep the beams in a ductile manner because they are the weak links, and accordingly we need to have the ductile detailing as per the Indian specification, as per IS code 13920, that whatever amount of reinforcement is there, that is 2 bars are going all through at the top level, you should have minimum 1/4 of the reinforcement, which is a 1/4 of the tension steel at the topmost tension zone at the beam column joint, where the 2 dots are being made. This is green and pink. This is the top tension zone of the beam column joint. Suppose let us consider it as AST. So you are required to keep AST by 4 at the compression zone of the beam, that is at the top of the beam, and you are supposed to keep whatever reinforcement is coming as per the actual analysis, or 1/4 of AST, whatever is greater of the two, you are supposed to keep that at the bottom, that is tension zone of the beam, and 1/2, that is AST by 2, you are supposed to keep at the bottom of the tension zone, where 1 dot in green coloring is being made. This is as per your Indian standard earthquake code 13920, because this is the thing, if the as per the analysis, the manual analysis, the things are coming out less, the reinforcement is coming less here, you are not going to consider that. You are going to consider AST by 2. Whatever tension zone reinforcement is coming, you are going to keep half of that. This is the way how we do the ductile detailing till 2D of, that means 2 times the effective depth of the beam. You are going to keep the stirrup spacing very less as compared to your middle zone, but not more than D by 2, which is being shown, that effective depth by 2 you can keep within those limitations, but not more than that. So this is the reason, that because most of the earthquake force is being followed, or being the behavior is like that, the beam column joint is having the maximum earthquake force. Most of the displacement is at that point. So we need to confine this part very much, whether it is beam column joint, whether it is column to column in between, or whether it is beam to beam in between. Lapping prohibited in regions where longitudinal bars can yield in tension. This is the reason, because this is the part above the beam column joint, or by the side of the beam column joint, that where the maximum displacement is there, maximum forces are there, and the maximum proposed opening of the stirrups is there. So we can't allow the lapping in these zones, because what they are going to do, they will let the reinforcement open up, and we don't have more confinement. The confinement is lost, and the complete column can be having a failure. Steel reinforcement columns in RC buildings, it has been shown here that the links are being rounded up inside. They are having 135 degree hoops, longitudinal bars along vertical line, transverse ties horizontally. So you need to maintain the vertical distance of ties also properly. It should be whatever it is being mentioned, 75 mm, or it should be less than whatever Indian standard 13920 code says. You are supposed to follow that. Two types of damages: axial flexural and shear failure. So it is going to be due to the large tie spacing. If you are not keeping the spacing of stirrups or ties vertically, maintaining, you are not maintaining that, in that case it is going to, you can have axial failure and shear failure. Even in between cross ties, you are supposed to maintain those distances, those whatever, if you are the levels, intermittent columns, intermittent longitudinal bars, you are going to decide where you are supposed to keep these cross links in between. IS 13920 1993 says that column width should be greater than 200 mm, is equal to 300 mm when center to center beam is 5 meter, center to center column is 4 meter. That means interstory spacing is 4 meter. Close transverse ties, horizontal shear force, excessive bending, these are the things which are being resistant due to close transverse ties. That is concrete splitting. These are the type of failures which are being safeguarded due to close spacing of ties. 135-degree hooks, closely spaced ties at two ends, that is larger dimensions of the columns. We need to keep 1/6 of the column height. That means this is the zone where we are supposed to keep the tie spacing very small. It should be 450 mm. Lapping vertical bars. This is the zone as it has been shown here, HC by 4. Okay, where we are required to, and at least larger of D, that is HC by 6 and 450 mm. So these are the specifications. This is the height at which we are supposed to keep the tie spacing very less, and we are not allowing the lapping of our longitudinal reinforcement in these zones. Again, the same as it is for horizontal structural elements. Lapping vertical bars in the middle half of the column is allowed because shear force is 0, as we see. Okay. Our moment is 0. Beam column joints in RC buildings. It is having very critical part to play in the earthquake resistance and earthquake transfer of loads. So we are required to keep the beam column joint very much intact even during earthquake is there in the building. So we are supposed to plan it accordingly. So there is a maximum confinement of the core inside that beam column joint. You are providing vertical as well as horizontal ties, which is confining that beam column joint to have the resistance in compression as well as in tension. Whatever horizontal bars are passing through it of the beam, and whatever longitudinal bars are passing through it of the column. Along with that, whatever ties we are having in horizontal and vertical direction, they all with the combined effect are going to confine the beam column joint to safeguard the building, because maximum they are going to confine, the more they will be able to transfer that forces to the vertical and horizontal elements. Reinforcing the beam column joints. This is how we do. We are putting extra effort in placing this horizontal ties in the beam column joint. This is the practice that we follow, that there is a particular system to provide these type of ties in the beam column joint. Once the vertical ties are being provided in the columns, and then horizontal ties which are extra as compared to the which there is in the beams. So there is a special pattern, there is special methodology to initiate how to do it. These are being shown in these steps. This is a wrong practice which we keep larger spacing to the ties, which is closer to the beam column joint, which is very incorrect, and it should not be it should be discontinued. Anchoring. Anchoring is also required to a larger extent to give the homogeneity and proper anchoring to the structural elements, horizontal to the vertical. Some of the good practices that you are allowing all the bars of beam to let it pass through the columns, because if you are playing with the sizes of the beams and columns, you are reducing the size of the beams, or you are reducing the size of the column. That means you are passing the reinforcement of the beams with a certain angle into the column, which is wrong. Your beam reinforcement is required to pass through the column straight. That is why what happens that some of the people reduce the sizes of the columns due to the architectural aspect. That is a wrong practice. Open ground story buildings, that is soft story mechanism, which we are required to remove. We should not do it. This is the inverse pendulum type of system. A complete mass which is quite high as compared to your ground floor stories is vibrating in a manner which is not required. We should avoid it. We should give a consistency to the mass which is we are providing in the upper stories, or if we are providing mass at the upper stories, we should equally provide that mass and stiffness to the ground floors also. Consequences of open ground stories in RC frame buildings. These are the consequences. This is the type of failures we can have. In the top left corner, it shows that we have a cripple failure where your reinforcement is standing, but concrete has fallen apart due to the reason that there is a change in column stiffness. Sudden drop of stiffness. This we have discussed that we are required to not do it. There should be a consistency of stiffness as well as mass throughout the building. Improved design strategies, that is IS 1893-2002 guideline. 2.5 times the force. In case you have not designed, that means obtained from only bare frame analysis, you have not used brick infills into your analysis, then in that case you are supposed to design your ground floor structural elements, that is columns, for 2.5 times the force. Short column damages, that is the mezzanine floor, you are supposed to keep the confining reinforcement, that is ties, along that zone for that mezzanine floor and wherever we have this kind of things. Buildings with short columns, you are supposed to keep the things as per the analysis. If you are having slender column, accordingly you are supposed to provide the confining reinforcement as far as longitudinal reinforcement. Short columns are stiffer. That is the reason that short columns are stiffer, and that is the reason they attract more earthquake forces and they are more vulnerable towards earthquake. So if you are having a short column in your structure, you are supposed to give extra consideration to that short column for design and analysis. These are some of the few types of short column effects in masonry as well as in RCC, which you are required to take care of, because they are going to hit the things. This masonry is going to hit this column at this point, and this is going to have the short column effect. The solution is that you are going to provide the extra confining reinforcement in that particular zone where you are having the mezzanine floor which is vibrating in isolation, and it can damage the column in that particular zone. Shear walls in buildings, that is you are providing shear walls in buildings to participate in your lateral load carrying capacity. If you are providing shear walls into your design, that your frame and your shear wall both are participating in the lateral load capacity, then in that case also you can decide whether what proportion you are giving your shear wall to be taking the lateral load. Most of the cases it is 70 to 30%, 70% shear wall and 30% your frame structure. That is the lateral load carrying capacity which the designers take. This is the configuration of the building that is suggested, that you are supposed to keep the shear walls symmetric all around the periphery. Even if you are using inside, the stiffness of the shear walls should be same in both the directions. These are some of the configurations we use: C-shaped, L-shaped, rectangular, RC, hollow around the elevators. Because in these cases, in the case of, as you can see in elevators, the stiffness of that particular shear wall is same in all the four directions. This is the boundary elements and the reinforcement arrangement of a typical shear wall. This is how we provide the staircase in our structures. We are required to provide it structurally not connected. If you are going to provide it structurally connected, it is going to damage first. You are required to keep it structurally disconnected as a separate unit. It is preferable and it is beneficial to keep it like that. You can keep it like that using different methods, as there are few which are being suggested by codes. You can keep a tread there, you can keep a beam which is being separated. Plan of the building should be simple. If it is complex, then you should provide an expansion joint in between. These are some of the suggestible shapes, and there are some of things. Not too long is not suggested, too large in span is not suggested, too tall is not suggested if not being properly designed and taken care of. Preferably, that is why it is written here, preferably if your purpose is served for a lesser height, then it is okay to provide lesser height. Inverted pendulum system, that is your mass is accumulated on the top stories more. It is not suggested. Discontinuity in your structural elements is not suggested, because it is going to discontinue the path of your force transfer from top to bottom. If it is going to be like that, it is going to hit your beam wherever it is discontinuing. It is not going to find any path of that energy transfer, and that particular structural element is going to be damaged, and directly then your building is going to be damaged. Pounding, you are supposed to keep the safe distance between the two buildings. Next, swimming pools, water tanks, they are lumped masses, huge masses of water which are not suggested on the top of the buildings. Even in 5-star hotels, it is not being suggested, but if they are being kept at the top floors of the building, they are supposed to be properly designed for the forces, whatever they are having due to the lumped mass of that water, whatever slashing and whatever effects they are going to have at the time of earthquake event. And if you are keeping a water tank at the top of the floor and the topmost floor at the roof level, you are supposed to transfer the forces which are going to come due to earthquake to the columns, and accordingly you are supposed to design those columns for the earthquake.
So here I would like to thank Dr. Anshu Tomar for delivering his talk.